Hey everyone, and how goes it? Welcome back to CSCE552 Game Development. I'm your instructor, Dr. JJ Shepard, and today we're going to continue our discussion around game development. In the past lectures, we have focused on the concepts and the roles related to game production. We discussed extensively the concepts related to game design. We focused previously on the iterative process of game design to create a game concept. For the producer, this has established the abstract major features of the game. Today, we start focusing on the concepts related to the game's concrete specifics. We now move to the game design pre-production phase. We now take our initial designs further and begin collaborating with more people to refine it. We have seen that creating the game concept starts with the game designer, but this collaborative and iterative process brings in more roles as the concept evolves. As we have seen, the game designer, with sometimes the assistance of a producer, creates the game concept from an idea. Later, programmers and artists are brought aboard to help further refine the specifics of the game. These new members may also assist in redesigning certain parts of the game concept during the development for a myriad of reasons. As we move past the concept phase, we now enter the pre-production phase. This typically starts with building a team. Games can either be created by a single person or more commonly by a team. Solo development describes a single person who creates a game. This includes both designing and developing the formal and dramatic elements. On the other hand, we have team development, which describes a team of people who create a game. This usually has separate people for each of the roles, and even describes some specialists within. There are pros and cons for each kind of team. For solo development, communication is simple, as you are the only person who is creating the game. Changing plans does not need approval of a team, as only one person is the team. This means that one person is in charge of everything that needs to be done. However, when one person does all the tasks, this can be very overwhelming, as creating all parts of a game is very time-consuming. When working alone, we have one perspective, and this can be limiting. One person creating something may miss something obvious to someone else. In the end, the biggest drawback is one person is in charge of everything. While this is also described as a positive, it can also be a big negative as well. There is nowhere to hide whenever one person is in charge and they fail. Team development has an obvious pro as tasks are shared by multiple members of a team. This also brings other perspectives which help refine and improve the game's design. In this way, a team is responsible for everything. However, introducing more people does add complication. For instance, communication is not as straightforward. Many new developers make a critical mistake in assuming that communication is simple and just happens. We need to organize this well and communicate effectively in order for this to work. When working in a team, changing plans requires discussion, as this may affect others' work. We must keep everyone up to date on all matters. Finally, a team is responsible for everything is a huge drawback. Once again, this was described as a positive earlier, but consider that a team is as only strong as their weakest member. If not everyone is contributing equally, then it can cause the entire project to fail. I would imagine each of us has had one of those group projects where one or more members did not do what they were asked. Regardless of which you choose, understand that there are trade-offs or pros and cons for each. I have worked both as a solo developer and within teams on a number of projects, and from my experience, there are positives and negatives for both. I recommend doing both if you have the time, but for this course, I would more recommend working in a team. It provides good practice and cooperation and takes the burden of needing to do everything yourself. Team building is all about finding the correct mix of people to bring your game concept to life. A person's talent and skills are key elements to consider. What are they already capable of doing, and especially already can do well, is important. Creating a game requires a variety of expertise, and these skills are acquired over time. Knowing someone's skills helps to select the correct members of your team. However, talent and skill can only go so far, as we need to find the correct mix of skills and personalities to work successfully. Humans are not deterministic machines. One person may communicate and work in a different way, but is still valid. Just because it's different does not mean it's wrong. We have most likely been in group projects in our past academics, and notice how some people like to work alone on tasks, while others crave attention of working with everyone. Some people are very rigid about their concepts, while others are more flexible in their approach. Some have big, boisterous personalities, while others have a more meek and mild temperament. All are valid, and finding the correct mix is central in making a project go smoothly. In selecting a team, consider everyone individually and ask, what do they bring to the project? And do they work well with others on the team? In addition, ask, does their actions match their words? Even outside of this class, that is an important detail to consider. However, within this class, we need to know that everyone is doing their part, or else the entire team will fail. As it may have been mentioned before, communication is fundamental to all of this. When it comes to forming a team, we must establish a means of communication early. I strongly recommend to centralize and organize all forms of communication. That way, details can be found in one place and not scattered around in different locations. One means of implementing this is by using a central chat client. Central in this case meaning that all members will use this chat client program to discuss the different parts of the game. There are many chat clients out there, and picking one and sticking with it is important. We also have a centralized game design wiki. This acts as the game design document, but allows for collaboration among the team members. While game design documents of old used to be long, immutable documents, more often, the GDD is now created as a wiki. This helps facilitate the iterative design process. This will also include the technical design document, the art list, and the schedule. Creating a version control for source code and assets early is also essential. As we have learned in past software engineering classes, version control is basically a database of files and their history. This allows us as developers to log changes and revert to previous versions when necessary. This also provides a centralized location for all of our source code and assets. We may also take advantage of features like branching and merging provided by version control software. Branching allows us to create a new working copy of a file so we can modify it without affecting the rest of the project. Later, the changes are applied from the branch by merging it into the main line of the project. The most common version control currently is Git, and many engines have Git integrations fully available. A bug database centralizes all the problems in one location. Of course, this helps the team to know what needs to be fixed. Commonly, we record the kind of error, the steps that caused the error, the results of the error, and the priority of the error. Intuitively, high-priority bugs deserve more immediate attention, and low-priority bugs can be fixed in the next iteration or patched later. Meetings undeniably are one of the best ways to communicate with a team. It is best to schedule meetings in order for them to be most effective. Establish recurring meetings that are scheduled either daily, bi-weekly, weekly, monthly, quarterly, etc. When something unexpected occurs, be willing to schedule emergency meetings. However, these should happen only when necessary. Not every error is an emergency. Not every unexpected event is a crisis. A good question to ask is, can this wait until the next reoccurring meeting? Clearly define a beginning and end times and stick to it. People's times are important. Do not waste their time. When scheduling meetings, also create a meeting agenda that features all the points of discussion. This keeps the meeting on task and avoids deviating on unimportant subjects. It is best to provide the agenda well before a meeting. This way the members can familiarize themselves on topics that will be discussed and provide better feedback. At the meeting, there is commonly a moderator who leads the points of discussion. You may think of them as the meeting referee. The moderator may also be the person who takes notes during the meeting about what was discussed. From these notes, they create a meeting summary, which is then shared with all the members afterwards. In all of this, we must keep all communication professional. Yes, we are making games and games are fun, but we are working hard as professional game developers. We take this seriously, and communicate professionally demonstrates that you are taking it seriously as well. It also works well with any audience, so make sure to practice communicating professionally. Here's some general advice when communicating with teams. Step up or step back is an exercise that can help someone with expressing their ideas to others and can help others listen to someone else. If you consider yourself to be a quiet person, then try stepping up and communicating your ideas. It can be scary, and it even can be embarrassing sometimes, but be brave and be confident that you know what you know and speak out. If you are someone who is more assertive or a loud person, then consider stepping back. Practicing listening to others is a skill that's acquired over time. Keep in mind that listening is not the same as hearing. You may hear someone, but not be listening to what they are saying. Keep an open ear and an open mind and a shut mouth can help you to understand someone's great suggestion. In group settings, some people may be good on paper, but not in practice. People can claim a lot, but can they deliver on it? Shared values, such as a good work ethic and dedication, are important in any setting. Always watch to see if someone's actions are lining up with their words, and do not ignore the negative signals or red flags. To be successful, it is all about dedication and participation. Be careful when you're working with friends. Just like before, watch their actions and see if they do care or if they're just saying it to sound nice. When providing suggestions, I recommend using "what if" instead of "do this." This allows more flexibility and agency when solving the problem. Speaking of which, when there is a problem, do not direct blame. Focus on the problem, not the person. Avoid saying phrases like "your code is bad" or "your animation is off time," and focus on the problem by saying, "the code for the inventory system is dropping the frame rate," or "the animation for the walk cycle is off somewhere in the middle." In this way, the person does not feel attacked and can more directly address the problem itself. The last example also demonstrates a self-evident piece of advice. When communicating, be direct and be specific. Ambiguity and vagueness leads to all sorts of problems, so make sure to practice communicating both directly and specifically. People cannot read your mind. Now that we have a team formed and our lines of communication established, it's time to start looking into the specifics. We move on to planning the game's production. we will turn our attention to the programmer's role in game design, but more specifically, the software design in relation to the technical design document. Now, we discuss game programming. We have learned that there are many different approaches to software engineering that involves the software development process. Creating a video game is an exercise in software engineering. This is a methodical process of developing and implementing software. We have learned that the lead programmer creates a technical design document, which details all the programming and other technical aspects of the game. A software development process helps to plan and manage tasks required to create software. Big projects require careful planning. Some common software development methodologies include waterfall development, agile development, and incremental development. The various software developing methodologies commonly involve gathering requirements for the software, designing and planning the software, implementing or writing the software, testing the software for quality assurance, deployment and maintenance. Most are performed in some order or repeat these steps, yet they mostly remain the same. Requirements are essential as we need to know what the game is and what the game does. We consider this to be the software and the game's features. Most games have some features that overlap, but also they have some features that are uniquely specific. It is important to identify both, as it helps us to move on to the software's design. The game concept developed by the game designer details all of the game's features that are required. Found in the game design document, this contains the formal elements of the game. This will become the code that implements the operational and constitutive rules for our game. As software designers, it is important to look how each of the formal elements, players' objectives, procedures, rules, resources, conflicts, boundaries, and outcome, can all be represented in terms of software code. The game's instructions become the software's instructions, so it is also important to look at how the game's instruction sections, abstract, materials, setup, turn sequence, win-loss conditions, and how that connects to the formal elements that can be represented as the set of software instructions. As communication is fundamental to all of this, we can see how we must communicate the game's instructions to both the player via well-composed words and to the computer via well-composed code. Keep in mind that while this details the features, it mentions nothing regarding the design or implementation. It is up to the lead software engineer to create a technical design document from the GDD. Values are important in any domain: family, business, and especially programming and design. As programmers, we learn values from our experience and from listening to our teachers and peers. When designing software, we've learned a few common values. Number 1, keep it simple. The more complicated design makes it harder to fix, change, or extend functionality. Number 2, write code that works first and refactor and optimize later. Avoid pre-optimization as it slows or stops progress. This is a common problem with many new developers. 3. Only use more advanced software engineering design, concepts, and structures when it's necessary. Avoid over-engineering a solution as it just wastes time. 4. Read everything twice. Read everything twice. Documentation, API, source codes, plans, requirements, diagrams, contracts, etc. Read over everything and make sure to reread it later on. Effective communication is about expressing ideas, but also slowing down and understanding the ideas. 5. Be aware and use the existing tools and software around you. If the wheel already exists, then do not reinvent it. As you may have heard, as programmers, we're not lazy, we're efficient. We find ways to create great works quickly and efficiently. Within programming and software engineering, we have learned a few common steps that help us. Step 1. Identify your data. What information do you need to keep in our memory? What information is variable and what information is constant? What is the kind of data? Numeric, words, strings, collections, other structures? Knowing that, we must use a programming language to communicate with the machines. How can we use the programming language provided data types to represent the data? This is always the first step, as all software is representative of information. We need to generalize information into very simple values such as numbers, words, collections, etc. From there, we must be aware of the common provided data types in most programming language, such as integers, floating point numbers, characters, and strings. Step 2. Notice how the data changes over time. This demonstrates how the software behaves. What are the noticeable patterns from input to output? Construct flowcharts for low-level logic. Flowcharts help us to see the logic behind the branching statements and loops. What are some common actions within these patterns? Can they be grouped and reused? Noticing commonality in these actions can assist in creating functions or methods which group together these commands into reusable structures. What features modify the data and how? This further assists in creating structures like functions or methods so that it can be used and reused in many parts of the software. UML sequence diagrams for larger scoped behaviors. How the software behaves alongside of other structures like classes and objects is when a sequence diagram may become necessary. 3. If this is enough to implement the requirements for the game or any software, then go no further and code the game. We do not need to over-engineer solutions, so if it's possible to write it simply, then just do it. No one is ever impressed with an over-engineered solution, and in fact, it just makes the person who did it appear to be a bad problem solver. When a very simple solution is not enough to implement all the features of a game, then we need to use a more advanced approach. This is where decisions in Step 3 is continued. Otherwise, we need to consider using more advanced software engineering techniques to better design a solution. Moving past that decision, this is where we, Step 4, group together or encapsulate related information into classes of objects. We always ask ourselves, how is the information related? And is it possible to group information into its own unique data type? As a programming language is meant to mimic a natural language, we look for possessive parts of speech like an apostrophe S in English in order to relate a group of objects together or encapsulate the data into more advanced data types. In object-oriented languages, classes are structures where the data and functionality can be grouped together to create instances that we call objects. This is the essence of object-oriented programming, where data encapsulation means to group together related data under a single data type and provide both access and modifications through the methods when necessary. The last part we sometimes just say we hide the data, and it relates to the same concept. Step 5. Develop functionality and methodologies that relate to the behavior of your objects. Objects can be viewed as nouns, and they perform actions or verbs. Functions or methods are typically grouped inside of classes to perform the actions related to the object's data. In fact, there were 6 easy steps to creating most classes. Once we have grouped together the data, we move on to Step 6. Further identify relationships between classes and determine where design optimizations may occur. Association, inheritance, polymorphism, and abstraction are a way we can better optimize and organize our code to be reused, shared, and create a cleaner design. With association, also called composition, this can be considered has a relationship between two object types. We think of this as one class contains a reference or references to other classes. With associations, we also have a different version called aggregation and composition, which are different and sometimes stronger forms of association. Inheritance can be considered the is-a relationship, and it extends a more general class into a more specific class. It works similar to biological inheritance, where the properties and methods of one class is passed to another. In fact, the base class is commonly called the parent class, while the inheriting class is sometimes called the child class. This hierarchy, which is implemented as a tree data structure, allows us to create extended specific versions of existing classes to better suit our specific needs. Polymorphism can be described as one becomes many, and is similar to inheritance, but more describes that this object does a certain method or class. It does not detail how, but we know the object implements these methods based on a programming interface. Much like how user interfaces are created so that users can interact with the software, programming interfaces, or just interfaces for short, are used so that programmers can interact with a pre-existing software system. When a class implements an interface, it ensures that the functions are implemented or written inside the class. A unified modeling language, or UML class diagram, shows the software structure by visualizing the classes and their relationship to others. A UML sequence diagrams show that the software's behavior by demonstrating how the data is passed and changed throughout the system. Once we have done some initial software design, we move to step 7. Determine if there exists software patterns that may assist in creating the solution. Many common well-solved problems may have solutions that follow a similar pattern. A software pattern is a general, reusable solution to commonly occurring problems within a given context in software design. There are broad software pattern categories, such as structure patterns, behavior patterns, creator patterns, concurrency patterns. We are only going to focus mainly on structure, behavior, and creator patterns when creating games. Understanding each of these, structure patterns demonstrate common reusable design relationships that exist between objects. Composition pattern, flyweight, facade pattern are types of structure patterns. Behavior patterns focus on organizing common actions and communications between objects. Iterator pattern, state pattern, observer pattern, command pattern are kinds of behavior patterns. Creator patterns are connected with the mechanisms that create objects. Singleton pattern, factory pattern, object pools are typical creator patterns. Games utilize some of each and also introduce some that are unique to games. Let's begin with how game software behaves. Most of us start learning procedural programming when we first begin our computer science journey. This is concentrated on the software behavior and how the data changes over time. First learning how to program games is no different. One behavior pattern that is unique to games is called the game loop pattern. We understand that time is a critical factor in all games. Games constantly need to provide feedback to the player by handling events, updating game objects, and drawing the results to a screen. Game loop pattern describes the common sequence of steps. 1. Handle events. 2. Update the data. 3. Draw the results. This decouples the progression of game time from user input and processor speed. For video games, no matter what the hardware that it's played on, it will still play the same way. Each game loop iteration progresses the game, and each step focuses on a critical aspect of this progression. The event step involves gathering information about occurrences that have happened since the last game loop iteration, and applying necessary actions related to the event. User input, collision detection, message handling are very common events. The update step modifies the data periodically based on the previous events and data. Moving the player, destroying an asteroid, collecting a coin are all examples of what happens during an update. The draw step displays the results of the update. Finally, this shows the player the results of their actions. In games, a frame is an abstract unit of time between each game loop iteration. Typically, one game loop iteration is equal to one frame, which is equal to one turn sequence iteration. Each frame progresses the game. Real-time games mean that the frame progression matches closely to actual time. Games that feature interactive movement like sports, real-time strategies, platformers, etc. Turn-based games mean that the frames progress only when a certain criteria is met. These are games that feature taking turns, such as RPGs, chess, etc. Frames per second, or FPS, is a way to measure the speed of a real-time game's progression. Often called frame rate of the game, a game that runs 60 frames per second performs 60 game loop iterations for all game objects for all their components 60 times every second. Practical time efficiency of code is a high priority in achieving good frame rate. There are steps that may appear to exist outside of the game loop pattern that we need to consider. The initialization event is when all the data or resource for the game are created and set to default values. This event only occurs one time, and it is to start the game loop. Within game code, this usually corresponds to a programming function called start, begin, or init. In contrast, the finalization event is when all the data is deallocated from memory. This also occurs one time to end the game loop. In code, this usually corresponds to programming functions called end, stop, or destroy. As both of these events only occur once, they could be considered outside the game loop, but in the end, they are just special kinds of events. Let's now see an example of this pattern using a previous game concept. We're going to focus on how to apply these steps to create code for our high-low game that was previously designed as a game concept. Reviewing this again, about. High-low is a classic puzzle game where the player must guess the correct value randomly picked in only a few guesses. Materials. A player, a referee. Setup. The referee selects a random value from a known range of values. For this example, let's assume that the range is from 1 to 100. The referee knows the player only has a fixed number of guesses. For this example, let's assume the maximum guess count is 3. The referee sets the player's guess count to 0. Turn sequence. Step 1. The referee informs the player that they have selected a secret number from the number range, and they only have a few chances to guess correctly. Step 2. The player then guesses a value. Step 3. The referee compares the player's guess versus the secret number. Step 4. The referee increases the guess count by 1 and checks it versus the maximum guess count. Step 5. The referee then tells the player if their guess was higher, lower, or equal to the secret number. Step 6. If the player's guess was equal to the secret number, then the referee informs the player that they have won and ends the game. Step 7. Otherwise, if the player's guessed higher or lower and is still below the guess count, then inform the player and repeat from step 2. Step 8. If the guess count is exceeded the maximum number of guesses, then the referee informs the player that they have lost and tells the player the secret number, and the game ends. Winning and losing. The player wins when they guess the secret value within a fixed number of tries and loses otherwise. Now that we have re-established the game, we can see and start identifying some of the game behavior right away. First, we notice that the setup seems to be very similar to the initialization event. This describes the data that is needed before we begin the game and only occurs once. Looking a little closer, we see this data seems to be some numeric value that is known to the system. These are declared and initialized during this event, and now we have set up the game loop into motion. We move to update. We have all the resources we need, and they have been updated to feature their default values. Now, we're ready for our first draw step. We notice in the turn sequence the first step is the referee telling the player that they have selected a number from a range, and they only have a few chances to guess correctly. We can consider this to be the first draw step, as the game official has informed the player what the game is and how to play it. We keep in mind that draw is a loose term for inform the player, whether it's visual, verbal, or by other means. Now we follow the loop back to the top, where we are waiting for the user input. This operational rule is another common event, like initialization, finalization, but it occurs more than just once. This is a commonly repeated event, much like collision detection and response. Once the user has made a guess, then the game progresses to the next step. Now we move to updating the data based on our constitutive rules. Step 3 mentions that the referee will check the guessed value versus the secret value. Following that, the guess count increases by 1, and that is checked versus the maximum guess count. We now draw the results based on the update step. The referee informs the player if their guess was too high, too low, or exactly correct. The referee then tells the player whether or not they have more guesses or if they've lost. Based on whether or not they have guessed the correct value within the given amount of guesses leads to the special finalization event. Once this occurs, the game is over and the game loop comes to a close. Commonly, this is used to deallocate resources that the game was using. We know from past computing courses that a flowchart can be used to show the software behavior. We typically put simple statements into boxes, decisions into diamonds, user input into slanted boxes, and arrows showing the flow or progress of the program. With decisions, we must remember to label true and false arrows showing the branching logic. Sometimes we may also use connectors or junctions represented by circles to make the overall design cleaner. Also, I commonly include special boxes for start and end. The game loop behavior pattern has been shown to be an abstract flowchart. Each step, events, update, and draw, has further details involved. When we develop our games, we can use these to help model and understand our game's logic and help to frame the operational and constitutive rules. Understanding this, we can model our game's behavior in a flowchart to look like this. Aligning our flowchart with the game loop steps, we can start seeing how this comes together. Notice how typically there is an event that is followed by an update and then followed by a draw. In this example, the specific kinds of events, initialization, user input, and finalization, were specified directly. We also notice that the steps are not strictly defined, meaning the sequence, events, update, and draw most commonly occur in that order, but in some cases it may omit one of those steps. For instance, we notice that after the user input event, there is an update followed by a draw, then followed by another update instead of an event. This is okay, as there is no need for an additional event between, so we can skip checking for an event. We may also decide that we could reorganize this logic to follow events, update, and draw pattern more directly. In either case, the logic is essentially the same, and the pattern works better being considered more flexibly than rigidly. Going back to the logic itself, we can then implement this in a variety of programming languages. The key understanding is the logic of the game does not change, and all we need to concern ourselves with is the implementation details related to each programming language. Here's an implementation of the game in Java. We start to notice how each of the parts are written or implemented in this coding language. Executing the code plays the game described. Similarly, here is the implementation of the game in C++. We see there are some differences in the code, but when it's executed, it plays the same game. Yet again, here's another implementation of the game, but this time in C#. Here's an implementation of the game in Python. We can see no matter which language this was implemented, including Basic 2 for the Commodore 64 computer, the steps are still the same. Design does not provide implementation details. We must figure those out when we are developing the actual code. Design provides overall guidance of what the software must require, and this is a simple game that does not need more than what has been created. However, if we were to create a more advanced game, then we need to consider some additional design and planning. It's easy to understand that more game features require more sophisticated software structural organization to better organize the behaviors and show the game loop pattern. Speaking broadly, video game or just game software is the entire collection of the game-specific code, library, systems, and engines that compose a video game. The game software system is the code which runs or drives the game. Typically, it is foundational software that calls or invokes the game loop pattern functions that we write in game-specific code. It contains software libraries used to write game-specific code. However, this is commonly considered separate from the game-specific code. As mentioned, it is foundational code that we build our specific games from. A game engine provides many of the features common in most modern games. We do not need a game engine to make a game, but as a developer, it can speed up the process. In future lectures, we will focus on game development structure patterns and how they work in a game engine. We keep in mind that game-specific code is the software specifically developed to create a game. It is separate from the game software system. Most commonly, it uses provided features and programming interfaces provided by the game system. A game engine is a software framework for developing games, and it includes the necessary software libraries and supporting programs. The engine contains graphics libraries, physics engine, input manager, audio manager, message passing, etc. A game engine, again, is not required for making games, but it may speed up development time. In most cases, the game engine can be considered as the game system. They both contain the necessary software libraries to create a game. They are both in charge of executing the game loop pattern. Some non-typical games may require the use of software and additional engines that exist outside of the context of a single game engine. We keep in mind that game software system is a broader concept and game engines are a narrower implementation. In this lecture, we focused on team building and on the concepts around software engineering, software patterns, and the game loop pattern. We also demonstrate how the game concept can be adapted to fit this pattern. In the next lectures, we focus more on software patterns commonly used in game development. With all that being said, go with the flow, and I'll talk to you next time. It's time for a bonus round. What are some of the pros and cons of solo development? Pros include communication is simple, changing plans does not need approval, one person is in charge of everything. Cons include one person does all the tasks, one perspective can be limiting, and one person is in charge of everything. What are some of the pros and cons of team development? Pros include tasks are shared. Others' perspectives refine the game's design. A team is responsible for everything. Cons include communication is not straightforward. Changing plans requires discussion. And a team is responsible for everything. What is team building? Team building is finding the correct mix of people to bring your game concept to life. What are the 3 parts of the game loop pattern? The event step involves gathering information about occurrences that have happened since the last game loop iteration and applying necessary actions related to the event. The update step modifies the data periodically based on the previous events and data. The draw step displays the results of the update. What is a frame in relation to the game loop pattern? A frame is an abstract unit of time between each game loop iteration. Now, let's look ahead using our forward vector. Now we are getting technical by looking at the details in the game design document and starting to consider how this will become the game's code. First, identify the data and how it will be represented from the sections in the game design document. Next, determine the game's behavior by observing how the data changes over time. Then, find ways to fit these behavior within the game loop pattern and model it using flowcharts. This helps us to understand the frame-by-frame progression of the game. Finally, include the flowcharts in the component list section of the technical design document. The next lecture will feature more details regarding this. With all that being said, I'll talk to you next time.